Today, in the first hour, we will solve problems on vectors. So we will start with simple problems about points, and then we will end up writing equations of space planes given certain data about the plane. These will be useful later when we do multivariable calculus. Okay, so let's say the first problem is determine if the following points are collinear. Collinear. So this means along the same line. Okay, so the points are A equals 2, 4, 2. So let me use the points that I prepared. Okay, so 2, 4, 2. So sometimes we write this as 2, 4, 2. And sometimes we write this as 2I plus 4J plus 2K. So I think in the exam you will be given this notation, but any notation is acceptable. Okay, so I prefer to use this notation since it is easier to generalize it to higher dimensions. The other points are 3, 7, minus 2, and C is 1, 3, 3. Okay, so this is the question. Okay, one way to look at this is you consider these 3 points arbitrarily in space. If they form a triangle, then the length of one side is less than the length of the sum of the lengths of the other 2 sides, and this is true for each of the sides. Okay, so we check this we check this first, and there are 2 ways to do this. The other one is you look at the vectors formed by these 3 points. You choose one of them as the base. From that point, you suppose you choose A. From A, you go to B. That's one vector. From A to C, that's another vector. These vectors define a triangle, or if you like, a parallelogram. Then you look at the cross ratio of these. That gives you the area of that parallelogram. If these these vectors are pointing along the same line, then the area is 0. Okay, so this. Okay, so these points. So this is one solution. These points lie on a line if and only if the sum of the sum of the 2 smaller distances is equal to the length of the largest, or the area of the triangle, which is half the parallelogram formed by these points, is 0. Okay, so we'll do both of them. So for this, so we calculate AB. Okay, so this is the first one. So let me just write the first one. This is square root 3 minus 2 square plus 7 minus 4 plus minus 2 square. So this is equal to square root of 26. Then you calculate AC. This is square root of 45. You calculate BC. This is square root of 3. Okay? So we check from these, we check that if square root of 3 plus square root of 26, is it equal to square root of 45? Okay, if you do this on your calculator, you immediately see that they are not the same. But suppose we are doing this by hand, then what you do is you square these. Okay, so square both sides. Okay, so if calculator or using our smartphone, we see that they are not the same. We see that they are not the same. Okay, so to see it the old-fashioned way, you square both sides and simplify and square again. And square again. And you obtain is 312 equal to 256. So not equal. So these lines, these points do not lie on a line. Okay, so that's how you do this with one method. And the other method, so this is method 1. Yes? To do what?
For example, for AB plus BC is equal to AC or AC plus another. There are three combinations.
But with one combination, you found that they are not on the same line. So why are you going to check the others? So with one combination, you chose one combination, and this tells you that they are not along the same line. They form a triangle. Okay?
We don't know the order.
You choose any order. You choose any order. If with one of the orders you discover that they are on a triangle, you are done. Okay? Try to think about it a little bit geometrically. Algebraically, you are right. Algebraically, we have to cover all angles. But that's why algebra and geometry go together. Check now that the points, okay, so A equals 0, minus 5, 5. B equals 1, minus 2, 4. And C equals 3, 4, 2 lie on a line. Okay? So in this case, again, let's do all solutions. In one case, I calculate AB. So this is square root 11. I calculate AC. This is 3 times square root 11. And BC, this is 2 times square root 11. Okay? So AB plus BC equals AC. They lie on a line. So they is the points, of course. Okay, so this is one. Okay, so we'll do, to warm up, we'll do another simple example. Okay, so let me do this. So this is find the vector that has the same direction as 6. So let's call this a name because we'll eventually use the name anyway, as U 6 minus 2 minus 3, but has length 4. Okay, so the idea of this simple example is to refresh our notion of direction. A direction is a unit vector. Okay, so that's just what we should learn from this problem. Okay, so the direction of the required vector is vector u divided by its length. Okay, a direction vector. So this is the only reason why we are doing such a simple example. A direction vector is a unit vector. Okay, that's the terminology. Okay, so here we have to calculate u. So you calculate this and you find that this is 7. Okay, you square those things, they add up to 49. So our required vector is, it has to have length 4 times the vector u divided by u, length of u. So this turns out to be, I'll just write the numbers, over 7 minus 8 over 7 minus 12 over 7. Okay, so the calculations are trivial, but just the message that when we talk about a direction, we are talking about a unit vector. Okay, so the next problem is to determine if vectors are perpendicular, orthogonal, or neither. So these are warm-up exercises from the book, which I picked up. So let me write this. So we have, I think, 3 cases here. Okay, so determine if the following points. So in our case, we are taking these as vectors, are orthogonal, perpendicular, or neither. Okay, so this is just an exercise to remember how orthogonal and orthogonal and perpendicular are the same thing. So let us change one of them to something orthogonal, parallel. Now this is just to, again, exercise in our mind to change from geometry to algebra. Orthogonal and parallel are geometric objects. Of course, we don't like to decide this by looking at them. Algebraically, you take the dot product or cross product. Okay, so before we give the points, recall if we have 2 vectors which I used u and v. Okay, so u dot v is equal to length of u times length of v times cosine theta. Okay, theta being the angle between them. Okay, so theta is the angle between them. Okay, so if they are orthogonal, theta is pi over 2, cosine pi over 2 is 0, so u dot v will be 0. Okay, if they are parallel, theta will be 0, but cosine 0 is 1, so you'll get a number here. By just looking at that number, you don't know whether the number appeared just like this or this. You have to do one more calculation to calculate these. But there is an easier way in that case. We have u cross v, which is u v sine theta. Okay? So when theta is 0, this catches it. When theta is pi over 2, this catches it. Okay? So conclusion, u and v are orthogonal if and only if u dot v equals 0 and u, okay, let's use this notation, parallel to v if and only if u cross v is 0. Okay, so these are rudiments of algebraic geometry where you answer geometric questions by algebra and nobody questions you because the numbers are there. Okay, so in our case, first numbers are u equals 9, 3, and v equals minus 2, 6. Okay, so here you check that u dot v equals 0. Okay, so they are perpendicular. Okay, so the legs, they are perpendicular, so here orthogonal. The next one given in the book is again the same u, 9, 3, v equals 3, 1. Okay, now we immediately see that 3 times this is this, so they are parallel. Okay, so here 3 times v is equal to u, so they are parallel. Also, you can now remember that cross product is only for 3 variables. Here we have 2 variables, but you consider them as z coordinate being 0. Okay, so also we look at I, j, k, 9, 3, 0, 3, 1, 0. So this is equal to 0. Okay, so they are parallel. And the other one is, let me finish it here. This time we have a vector minus 5, 4, minus 2, and v equals 3, 4, minus 1. Okay? They are not parallel because if lambda times this is equal to this, since the second coordinates are the same, lambda must be 1, but 1 times this is not this, so they are not parallel. Now we check dot product, so let me do this. U dot v, okay, so I dotted them, that's equal to 0, not orthogonal. And clearly, u is not lambda times v, so not parallel. Okay, so you can also calculate the cross product here, but that is some calculation, more calculation than your observation here. Okay, so let's come to something a little bit less trivial. At least we have to solve some equation. So in this problem, we have a fixed vector and a variable vector. We want to change the variable, so the angle between these two vectors will be as we wish. So this requires, the easy way to do this is the dot product. Okay, so this is 4. So let me write these things. There's find x such that the angle between the vectors so the vectors are A equals 2, 1, minus 1, and B equals 1, x, 0 is 45 degrees. Okay, so when we are talking about degrees, we explicitly write the degree sign there because all calculations in calculus all trigonometric calculations in calculus are in radians. When we are using radians, we don't write anything there. We just write, if this was 45 radians, we'll just write 45. Okay, so remember the reason for this is that when we derived the derivative rules to make life easier, we wanted to have that the derivative of cosine is sine, derivative of sine is cosine, and you put a -1 at an appropriate place. Okay, so this also follows from behind this. We have the fact that sine x over x as x goes to 0 is 1. Okay, so we want it to be 1. If you use radians, the limit is 1. If you use degrees, the limit is different. Okay, so that's why to make these coefficients 1, we chose to work with the radians. So when we say 45 degrees, and if we are going to do some trigonometric calculations, in your mind you have to transfer everything to radians. Okay, so in this case, of course, the problem reduces to dot product. Okay, so we know that A dot B is the length of A, length of B, cosine theta, and we want to fix x such that theta is 45 degrees. That's the algebraic formulation of this. Okay, now you calculate these things. A is, the length of A is, I found this to be square root 6. The length of B, of course, must have x in it. It turns out that this is square root 1 plus x squared. And A dot B is 2 plus x. Okay? And of course, I calculated this, and of course I have to write cosine 45 degrees is 1 over square root 2. So this is pi over 4, cosine pi over 4. Okay. So we put this, so we have, putting these things in, 2 plus x is equal to square root 6, square root 1 plus x squared, and cosine theta is 1 over square root 2. Okay, so we have one equation in one unknown. If we are lucky, we can solve it. Okay, since it will involve squares, we will be able to solve it. Okay, so simplifying this, let me see. Okay, so we have time, but you see the calculations are easy. You simplify this. Simplifying, we get, okay, eventually you get this, putting things on both sides. You have 2x squared minus 4x minus 1 equals 0. Okay, so this gives you 2x. So this gives you 1 plus or minus square root 6 over 2. Okay, so these are the two x's. Which may, so you get two vectors which have this angle with this given vector A. Okay, any questions so far?
Don't we have a length at that recall?
Huh?
The cross product.
Mm-hmm.
The cross product, the recall section. Recall.
Where is recall?
Yes. Don't we say the length? There?
Yeah, the length. Yeah, you are right. Okay, so thank you. Okay, so now next, find two unit vectors that make an angle of 60 degrees with the given vector. Okay, so here we will find two vectors which make that angle, and then we are asked to find unit vectors, so we'll divide the length. Okay, so let me see. Let me go over here now. Okay, so maybe I pass to more interesting problems. Okay, so let's do this one. This is also interesting. Find two unit vectors that make an angle of 60 degrees with our nice vector v. Okay, let me use this notation to tell you that we can use any of these notations. Okay, so our required vectors are of the form A, B. Okay, we have the A square plus B square equals 1. So this is for unit vector. And, okay, right here. And A, B dot product with 3, 4 is equal to length of AB. We know that this is 1. Length of 3, 4. We'll calculate this times cosine theta. Okay, so this one is 1 because we choose this as a unit vector. So you calculate this. This is 5. Okay, so we all know this nice Pythagoras stuff. 3, 4, 5 triangle. And cosine of 60 degrees is 1 over 2, right? 1 over 2, since theta is 60 degrees, or pi over 3 radians. Okay. So this equation becomes, so this one we also calculate. This is 3a plus 4b. Okay, so our equation, taking this 2 to the other side, we have 6a plus 8b equals 5. Okay, so we have this equation and we have this equation. Two equations in two unknowns. Again, if we are lucky, we solve them. But here, one of the equations is linear, so you solve one of them from here, put it into the other. So from here, you take b equals 5 minus 6a over 8. Put this into a square plus b square equals 1, and solve. Okay, so let's see. To cut the long story short, we get 100a squared minus 60a plus minus 39 equals 0. And this gives you a equals 3 plus or minus 4 times square root 3 divided by 10. And b from here, so you see when you are putting a inside b, you change the sign. So when you have plus here, you must have minus here. So it becomes 4 minus or plus 3 square root 3 over 10. Okay, so the required vectors are of the form AB, where A is this or this. Okay, so that is for simple problems. Okay, now let's come to more typical problems that we will use. So the next one is to find the area of the parallelogram in 3 space given by 4 vectors. Okay, of course you have to check that they really form a parallelogram. If they don't, then you just cross the problem out. Okay, so 6, find the area of the parallelogram with vertices. Okay, so P is 1, 0, 2. Q is 3, 3, 3. R is 7, 5, 8. And S is 5, 2, 7. Okay, so I picked these exercises from the book, so these are the numbers given in the book. Okay, so you see that we started to obtain non-trivial things because these are 4 points in 3 space. Okay, so if this was in the plane, then, okay, if you are lazy, you say I can draw triangles and find the area easily. But now this is some oblique shape in 3 space. We don't even know if the claim is true, if they are really forming a parallelogram or not. So we have to check, and once we are convinced that they form a parallelogram, we want to find the area. Okay, so pick any of these points as your base, whatever base means. Okay, so pick P. Generally, the first one is chosen. Even if this one was given here, you would probably choose that one because we will subtract this from the other vectors. You want to choose someone with small entries. Okay, so laziness is always popular. So consider the vectors. So PQ is 2, 3, 1. PR is 6, 5, 6. And PS is 4, 2, 5. Okay? So now our parallelogram, if it's really a parallelogram, our parallelogram is here. Okay, so we found these 3 vectors, so parallel. We carried this to the origin. We found this vector, and this vector. Okay, so we check now really that this vector is the sum of these two. So here, from here, we have PQ plus PS is PR. That's what I wrote here. So let's check PQ and PS. Yeah, okay, so the sum of these gives you this. So these points really define a parallelogram. Okay, so you have to check. Just because somebody wrote there that they form a parallelogram doesn't make it a parallelogram. Now we know they form a parallelogram. Okay, so I repeat again that suppose this is the origin. Those 4 vectors are these vectors from here to here, from here to here, and from here to here. By subtracting this vector from each of them, I carried this to the origin, and I have one of them is PQ, one of them is PS, and this diagonal turned out to be PR. Okay, so we know that the parallelogram is formed by these 2 vectors. So we'll take their cross product and find the area. Okay, so the area of the parallelogram is absolute value of PQ cross PS. Okay, so PQ, we calculate PQ cross PS. This is IJK. PQ is 2, 3, 1. PS is 4, 2, 5. And I calculate that to be 13 minus 16 minus 8. And the absolute value of this, okay, when you are talking about a vector, the absolute value means the length of it. Okay, so we don't want to introduce too many notation terminology. So this is square root of 269. So if you are interested, this is approximately 16.4. Okay, so this is the area. Okay. So actually, we want the area of this parallelogram. We carry it to the origin and calculated this area there. That's what algebra did to us. You have a question?
Why PQ and PS has to equal PR?
Because we are checking if these things form a parallelogram. Here is one vector. Here is the other vector, PS. We are at the origin now. Okay, so their sum. So this vector is PQ plus PS, and this is the parallelogram. If the vector given here, PR, is not in this plane, if it is something like this, or if it is pointing at some other point, then these 4 points in space are not forming a parallelogram. Okay, so 3 of them, obviously 3 of them form a triangle. The other vector is here. Okay, so we want to check that the other vector is also pointing in the right corner. Okay, so maybe instead of 70, you mistakenly write 71 here, and then if you do this calculation, you'll get a number here. Okay, this number is not the area of anything. So this number is the area of the parallelogram formed by these 2 vectors, but not the area of the shape given by those 4 points. Okay, so that's why you have to check. Okay, so let me check. Okay, let me do one parametric equation for a line, and then I want to solve something about a plane. So find vector, parametric, and symmetric equations of the line. So equations of the line through the point 0, 14, minus 10, and parallel to the line given by x equals -1 plus 2t, y equals 6 minus 3t, z equals 3 plus 9t, where t is a free variable. Of course, if you find any of these equations, you have total understanding of the line. But just as an exercise, we'll write, after we find one of them, we will write the other equations also. When the data is given like this, the easiest way is to find the vector equation. Okay? So the direction of this line, since it is parallel to this line, is these numbers here. Okay, so is 2 minus 3, 9. Okay, this line passes through this point and points in this direction. So we want this line to point also in the same direction. So you write it here. Okay, it passes through this point. A vector equation is, okay, let's say, sometimes we say, since this is a line, sometimes we say LT. If we want to denote position, we say P. And in physics, sometimes we write RT. Okay, so let's say LT. It starts first. So remember that a vector equation is describing an address. So how do you describe the address for a typical point on this line? You say first go to this point. Okay, so 0, 14, minus 10. Then follow this direction in any way you like. So this is the parameter, 2 minus 3, 9. So you simplify this. This is 2t, 14 minus 3t, minus 10 plus 9t. And you mentioned that t is free. You can move freely on this line. This is the vector equation. Now all the information is here. Parametric equation is to write this in this form. Okay. So this exercise is refreshing the terminology. Parametric equations. So x is equal to 2t, y is equal to 14 minus 3t, z is equal to minus 10 plus 9t, and you have to mention this. And symmetric equations. The definition for symmetric equations is eliminate t. So this is eliminate t. So this is x over 2 is t, and this is y. Well, minus here, y. Oh, okay, let me put minus underneath. Okay, y minus 14 over minus 3 is equal to z plus 10 over 9. Okay, so these are the symmetric equations. So the purpose of this easy exercise is to show that you can write any of these you like. Starting from any of them, you read every information about the line. Okay, so my favorite is, of course, this one. I don't know why I said of course, but I prefer that one. Okay, so now since we are about to finish, let me find a nice exercise about planes. Okay, so let me do this one. Now you want to write the equation of a plane with some data given. We know that the equation of a plane requires, in our algebraic presentation, two pieces of information: the direction which is perpendicular to the plane, and at least one of the points through which the plane passes. Okay, so this information is required to write an equation for the plane. We keep saying that an equation, not the equation, because if you write an equation for the plane, multiply both sides by 5, 55, 37, they all give the same equation. And there's no standard way of describing this. We cannot say always make the coefficient of z1, because sometimes the coefficient of z is 0. You cannot make it 1. Okay, so we just leave it free. Write an equation. Okay, so we'll give whatever data is given for a plane. When you want to write it from that collection of information, you have to extract two pieces of information: a direction perpendicular to the plane, and at least one point which lies on the plane. Then you immediately write the equation. Okay, so this problem is now maybe the last problem for this hour. Is given the line. So the line is given with this expression: x equals 1 plus 2t, y equals 3 plus 4t, z equals 5 plus 6t, where t is a free real variable, and the points a equals 7, 8, 9, and b equals 10, 11, 12. Okay, given this information, write an equation of the plane. Okay, so now we say the plane, because with this information there is a unique plane which contains these points. Okay, so we need to know at least one point through which the plane passes. We have two, so we'll pick one of them arbitrarily. And is parallel to the line. Okay, now the first information is trivial. We'll just pick one of these things. The other information we need is a perpendicular direction to the plane. Okay, so from this information we have to find this. First of all, when these 2 points are given, the vector from one to the other lies in the plane. So that's another direction parallel to the plane. This direction 2, 4, 6 is parallel to the plane. Okay, so we have two vectors. If we are lucky, these two vectors are different. then their cross product is perpendicular to the plane. So that will be the other information. Okay, so that's how we solve this in our mind. So let us now write. You see that I gave these numbers trivially, and sometimes when you give these numbers in this way, something may be 0, but let's check. Okay, so the picture is this. We have this point A, we have this point B. So this vector, say AB, which is B minus A, is parallel to the plane. And this point, and we have at the origin we have 2, 4, 6 is another vector parallel to the plane. Okay, so from here, their cross product is orthogonal to the plane. Okay, so once we do this, after we do this calculation, we know these two crucial information about the plane. We have an orthogonal direction, and we can choose one point on the plane, and we write the equation. Okay, so let us look at this thing now. Okay, so B. Okay, so this vector, so 2, 4, 6 is equal to 2 times 1, 2, 3. Okay, so I'm trying to make numbers. If you are doing this with computer, you don't have to bother with this. You just give this one. But since we are going to multiply this determinant by hand, I'm trying to choose small numbers. Okay, so 1, 2, 3 is parallel to the plane. So this is the direction of the line. And then we have AB is equal to 3, 3, 3. Okay, so this one is 3 times 1, 1, 1. So 1, 1, 1 is also parallel to the plane. Now I take their cross product. Okay, let W be something like this, I, J, K, and I use 1, 1, 1, 1, 2, 3. I multiply these, I get 1 minus 2, 1. This is orthogonal to the plane. Okay, so let me finish here. Take any point on the plane, say this one, 7, 8, 9, 7, 8, 9. Okay, an equation for this plane is, this is W. Okay, so let me put an arrow here so that it looks smarter. Okay, it's W dot x, y, z. An arbitrary point is going to be on this plane if it is dot product with W is the same as its dot product with any other point on the plane. Okay, so this is equal to W dot 7, 8, 9. Okay, so if you simplify this, well, simplifying is just multiplying these things, you get that is x minus 2y plus z is equal to 0. Okay, you check that this product is 0. So instead of this, you choose this. If we did all these calculations correctly, this dot this is also 0. Okay, check that, that's also 0. Okay, so this is the equation. Okay, so that's another way to check that along the way you didn't make a mistake in calculations. The dot product of this with this point and with this point must be the same, because that's the idea of writing an equation in this form. The dot product, given a fixed vector, the set of all points whose dot product is the same with this one is a line. Okay, so these are some problems to refresh our memory about this rudimentary analytic geometry. We'll use this later on when we do multiple variables. Okay, so that's all for this hour. Next hour, we'll pass to space curves.